Hi, my name is Jin. Now, I would like to explain about the scheduling algorithm. Scheduling algorithm play a crucial role in the efficient management of computing resources within an operating system. These algorithms are responsible for determining the order in which process or tasks are executed by the CPU, contributing significantly to system performance and responsiveness. The primary objective of scheduling algorithm is to optimize resource utilization, enhance system throughput, and reduce latency. Advantages of scheduling algorithm include improved system efficiency, enhanced user experience through faster response time, and fair distribution of resources among computing processes. Additionally, effective scheduling contributes to increased overall system throughput and allows for the concurrent execution of multi-tasks. However, scheduling algorithms also come with certain disadvantages. For instance, some algorithms may prioritize certain processes over others, leading to potential fairness issues. Additionally, the complexity of implementing and managing complex scheduling strategies can impose overhead on the system itself. Operating systems employ scheduling algorithms in various contexts, such as time-sharing systems, real-time systems, and multiple process environments. Time-sharing systems benefit from scheduling algorithms that provide fair access to the CPU for multiple users or processes, ensuring a responsive and interactive user experience. On the other hand, real-time systems require scheduling algorithms that can meet strict time limits to ensure timely execution of critical tasks. The working of scheduling algorithms vary based on their specific design and goal. In general, this algorithm allocates CPU time to process based on predefined criteria such as priority level, timeline, or the round-robin principle. They may use preemptive or non-preemptive strategy, where preemptive algorithms allow the interruption of currently execution process to give way to higher priority tasks. Non-preemptive algorithms, in contrast, allow a process to complete its entire execution before the next one begins. Round-robin scheduling is a widely used preemptive scheduling algorithm employed by operating systems to efficiently manage the execution of processes in a time-sharing environment. In this approach, each process is allocated a fixed time quantum or time slice, and the scheduler cyclically assigns the CPU to each process for each allotted time. This silent rotation continues until all processes have had an opportunity to execute, promoting fairness and responsiveness in multitasking systems. Round-robin scheduling utilizes a queue of processes with fixed time quantum for execution. The scheduler cycles through the queues, allowing each process to run for a specific amount of time. Complete process move to the back, and if a time quantum expires, the scheduler moves to the next process. This is repeated until all processes have executed. Round-robin scheduling uses a curricular queues and assigns a fixed quantum time to each process. The process gets CPU time for each slide, and if it completes, it goes to the back of the queues. If not, it is suspended and the next process is scheduled. Now, I would like to answer question about the round-robin. In the following question, there are 6 processes named P1, P2, P3, P4, P5, and P6. Their arrival time and burst time are given below in the table. The time quantum of the system is 4 units. Initially, at time 0, process P1 arrives, which will be scheduled for the time slice 4 units. Hence, in the ready queue, there will be only one process P1 starting with CPU burst time 5 units. So, the P1 will be executed for 4 units first. Meanwhile, the execution of P1, 4 more processes P2, P3, P4 and P5 arrive in the ready queue. P1 has not completed yet. It needs another 1 unit of time, hence it will also be added back to the ready queue. After P1, P2 will be executed for 4 units of time, which is shown in the Gantt chart. During the execution of P2, one more process P6 is arrived in the ready queue. Since P2 has not completed yet, hence P2 will also be added back to the ready queue with the remaining burst time 2 units. After P1 and P2, P3 will execute for 3 units of time since its CPU burst time is only 3 seconds. Since P3 has been complete, hence it will be terminated and not be added to the ready queue. The next process will be executed is P4. After P1, P2 and P3, P4 will get executed. Its burst time is only 1 unit, which is less than the time quantum, hence it will be complete. The next process in the ready queue is P5 with 5 units of burst time. Since P4 is complete, hence it will not be added back to the queue. P5 will be executed for the whole time slide because it requires 5 units of burst time, which is higher than the time slide. P5 has not been completed yet. It will be added back to the queue with the remaining burst time of 1 unit. The process P1 will be given the next turn to complete its execution. Since it only 1 unit of burst time, hence it will be complete. P1 is complete and will not be added back to the ready queue. The next process P6 requires only 4 units of burst time and it will be executed next. So P6 will be executed for 4 units of time till completion. Since P6 is complete, hence it will not be added again to the queue. There are only 2 processes present in the ready queue. The next process P2 requires only 2 units of time. So P2 will get executed again, since it only requires only 2 units of time, hence this will be complete. Now, the only available process in the queue is P5, which requires 1 unit of burst time. Since the time slide is 4 units, hence it will be complete in the next burst. So P5 will get executed till completion. The completion time, turnaround time, and waiting time will be calculated as shown in the table below. The formula calculates turnaround time use completion time minus arrival time. So 17 minus 0 becomes 17. 23 minus 1 becomes 22. The below also same. And then the formula calculate waiting time is use turnaround time minus burst time. So 17 minus 5 become 12. 22 minus 6 becomes 16. And below also same. And then to calculate average waiting time, plus all the number per 6 become 76 per 6 unit. That's all my presentation. Thank you.
Thank you. My name is Anglia and I'm going to present about preemptive priority. Preemptive priority scheduling is a dynamic scheduling algorithm employed by operating systems to manage the execution of processes based on their assigned priority levels. In this method, each process is assigned a priority values, and the scheduler continually assess and adjust the execution order based on these priorities. The preemptive nature of the algorithm allows higher priority tasks to interrupt the execution of lower priority ones, ensuring that critical processes are given precedences. This approach is particularly valuable in environments where tasks were varying levels of urgency and importance. To implement preemptive priority scheduling, each process is assigned a priority, typically based on factors such as task importance, deadlines, or resources requirements. The scheduler then organizes the processes in a quick according to their priority levels. During execution, if a process with a higher priority becomes available or if a new process with a higher priority enters the system, the scheduler preemptively interrupts the currently running process and switches to the one with higher priority. This allows for a flexible and responsive allocation of CPU time of critical tasks. The functioning of preemptive priority scheduling revolves around the continuous evaluation of process priorities. The scheduler maintains a dynamic priority queue, and the process with the highest priority is selected for execution. If a higher priority process arrives or if the priority of the existing process increases, the currently running process is preempted, and the CPU is allocated to the higher priority task. This preemptive mechanism ensures that time-sensitive or crucial processes are promptly addressed, contributing to improved system responsiveness. However, it requires careful consideration of priority assignment to prevent issues like priority interversion or starvation, where certain tasks may delay or neglected in favor of higher priority ones. Let's solve the example of the task. There are several processes P1 until P7 are given. The respective priority arrival time and burst time are given. Let's talk about the solution. First, we draw a Gantt chart. At time 0, P1 arrives with the burst time unit of 1 and priority of 2. Since there is no process is available, hence this will be scheduled until the next job arrives or its completion. At the time 1, P2 arrives. P1 has completed the execution and no other task is available at this time. Hence, the operating system has to schedule it regardless of the priority assigned to it. The next processor P3 arrives at the time unit of 2. The priority of P3 is higher to P2. Hence, the execution of P2 will be stopped and the P3 will be scheduled on the CPU. During the execution of P3, three more processors P4, P5, and P6 become available. Since all these three have lower priority with the current process, so we will wait until P3 to complete. After P3 complete, P5 will then schedule with a higher priority among the available processors. Meanwhile, the execution of the P5, all the process is available and ready to go. At this point, the algorithm will start behaving as non-preemptive priority scheduling. Hence now, once all the processes get available in the ready queue, the OS just took the process with the highest priority and execute till the completion. In this case, P4 will be scheduled and be executed till the completion. And here, since P4 is complete, P2, P7, and P6 will be scheduled in the processor until all the tasks is complete. After each process is complete, let's talk about the average waiting time. The average waiting time is to add on every waiting time and divide by the process number. As we can see in this example, it's 63 divided by 7 and that's 9 units. And that's all for me. I will pass my mic to another teammate. Thank you.
Hello, madam. My name is Soyoung Se. Today, I would like to talk about dynamic partitioning placement algorithm. Dynamic partitioning algorithm in memory management efficiently handle variable size memory allocation. Available memory is divided into variable size partition, and the algorithm select an appropriate partition to allocate memory for new or existing processes, adapting to their varying memory needs. This approach minimizes fragmentation and optimizes overall memory utilization. One notable advantage of dynamic partitioning is its flexibility in augmentation variable size processors, allowing for efficient utilization of memory resource. However, it comes with certain drawbacks. External fragmentation. can occur over time as memory becomes allocated and deallocated, leading to inefficient use of available space. Moreover, the process of selecting suitable partitions for allocation introduces additional overhead and complexity to memory management, impacting system efficiency. Dynamic partitioning placement algorithm find application in modern operating systems, particularly in scenarios where processors inhabit diverse memory requirements. It is commonly used in systems that support multitasking and variable size processors, allowing for a more adaptive and responsive allocation of memory. Dynamic partitioning divides memory into variable size partitions for processors of different size. When a new process starts, the algorithm finds a partition to accommodate its memory needs, using strategies like first fit, best fit, or worst fit. After a process completes, flash space may cause external fragmentation. Compaction techniques can be used to shift processes and reduce fragmentation, optimizing memory utilization in modern operating systems. Next, I would like to introduction of first fit. First fit is a memory allocation algorithm used in dynamic partitioning, a memory management strategy employed by operating systems to efficiently allocate memory to processors with varying size requirements. In the context of dynamic partitioning, the variable memory is divided into variable size partitions, and the first fit algorithm is responsible for selecting the available partition that is large enough to accommodate a newly arriving process. This simple yet efficient approach aims to minimize the search time of a suitable partitions, facilitating switch memory allocating. To implement the first fit algorithm, the operating system maintains a list of variable memory partitions. When a new process is initiated and requires memory, the algorithm scans the list from the beginning and allocates the first partitions that meet the size criteria of the process. If the select partition is less than the required memory, the remaining portion becomes a new partitions. The process continues until a suitable partition is found. While this strategy minimizes such time, it may contribute to external fragmentation over time as memory is allocated and deallocated. The working principle of the first fit algorithm is straightforward. When the process requires memory, the algorithm begins scanning the list of available partitions from the start. The first partition encountered that is large enough to accommodate the process is allocated to it. The remaining portion of the select partitions, if any, become a new partition available for future allocation. This process allows for quick allocation of memory, but may result in fragmentation over time, as similar partitions may remain scattered throughout memory after process complete their execute. To address this, compaction technique or other allocation strategy like best fit or worst fit may be considered. Despite its potential for fragmentation, the simplicity and speed of first fit make a practical choice for certain memory allocation scenarios in dynamic partitioning system. So let me see the question. In the question, there are 5 partitions in the memory, 3 partitions have processor inside them, and 2 partitions are hosts. The process requests are given as 25,000, 50,000, 100,000, and 75,000. Now, let us see how the first fit algorithm performs for the problem. In the case of the 25,000 solution, the algorithm scans the list until it identifies the first hole that is sufficiently large to fulfill the 25,000 requests. It then allocates 25,000 from the free space in the second partition, leaving 50,000 as a whole. In the case of the 50,000 solution, the 50,000 requirement can be fulfilled by allocating the third partition, which is the 50,000 in the size, to the process, not additional free space in generator. For the 100,000 solution, the algorithm satisfies the 100,000 requirement by utilizing the fifth partition, which has a size of 175,000. It allocates 100,000 from this partition, leaving a 75,000 hole. In the last solution for 75,000, the available free partition of 75,000 is efficiently allocated to the process with a corresponding demand for the same amount of space. Employing the first fit algorithm ensure ultimate fulfillment of the entire request, leaving no unnecessary or unsure space. So this is all for my presentation. Next, my friend will continue our presentation, talk about the worst fit. Thank you.
Hi, my name is Han Yun. Now I want to explain about the worst fit. Worst fit is a memory allocation algorithm utilized in dynamic partitioning, a memory management approach employed by operating system to differentially assign memory to process with diverse size requirements. In dynamic partitioning, the available memory is divided into variable size partition, and the worst fit algorithm aims to minimize fragmentation by selecting the largest available partition to accommodate a newly arriving process. Despite its counterintuitive name, WordFit focus on maximizing the remaining free space in memory after allocation, aiming to reduce the likelihood of small free blocks. To implement the WordFit algorithm, the operating system maintains a list of available memory partitions when a new process is entitled and requests memory. The algorithm scans the list to find the largest available partition that can accommodate the process. The selected partition is then allocated to the process, and any remaining free space becomes a new partition. Where worst fit might contribute to larger internal fragmentation due to allocating large partitions. It aims to minimize external fragmentation and enhance overall memory utilization. And however, the world-fit algorithm operated by seeking out the largest available partition during the memory allocation process. When a new process requires memory, the algorithm scans the list of available partitions and selects the largest partition that is still larger than the processor size. By allocating the world-fit largest bit, the algorithm attempt to minimize the creation of small free blocks, which can contribute to external fragmentation over time. Where worst fit may lead to external fragmentation, it strives to optimize the overall of memory, reduce the impact of free space. Managing free space efficiently is crucial for dynamic partitioning systems, and WordFix addresses this by prioritizing the allocation of larger memory blocks to income process. And now I want to explain about this question, example question. Job A have 44K, job B 220K, job C 614K, job D 64K, and the memory block list. Block 1 have 250K, block 2 800K, block 3 218K, block 4 have 200K, block 5 have 515K. And in the worst-fit memory allocation strategy, allocated memory to the largest available block that can accommodate the job. Here is how can allocated the memory block to the job based on the work-fit strategy. Job C 640K allocated it to block 2 18K since it is the largest block available. Job B 220K allocated it to block 515K since it is the largest block available. Job D 16K allocated it to block 3 218K since it is the largest block available. Job A 14K allocated it to block 4 200K since it is the largest block available. And now the memory blocks are allocated to the job based on the work-fit strategy. Thank you.